So up to this point, we talked about how layer 2 switching and classical Ethernet works on the ACI. How do we attach to access servers on the outside? How do we attach to layer 2 trunks, whether we're either extending the endpoint groups out of the ACI or whether we're using the external bridge domain, which is the L2 out. And in this section, we're going to talk about how do we extend the routing domain, the layer 3 domain, outside of the ACI. Because as we know, the data center is not going to be an isolated environment. We're going to have whatever our applications are and need to be publicly accessible via the WAN or publicly accessible via the internet. So somehow we're going to have to route our traffic into the fabric from the external network. Now, as we talked about earlier in terms of the overall capabilities and kind of the limitations of the system, one key point about ACI, which we'll see is kind of similar to how the UCS system works, is that it's not designed to take a full routing table. So it means that your outside layer 3 connectivity, typically you're going to have a default route that's going out to the WAN. You might have some sort of subset of your internal routes that are for the regular internal routing table. But the upper limit in the current version is somewhere around 40,000 IPv4 prefixes, which, as I mentioned before, the current global BGP table for regular IPv4 routing is about 700,000 routes. So it means that when you're advertising the routes to ACI, typically you're going to advertise some sort of summary or advertise just a default route where we have one or multiple potential exit points out of the fabric in order to get to the regular layer 3 routed network. Okay, so specifically we'll see that with the ACI design, it supports 3 different types of layer 3 interfaces, just like standalone NXOS mode or just like Catalyst or regular iOS platforms do, where we have our native layer 3 routed interfaces, where from a regular standalone NXOS mode, this would be our no switch ports. Then we put our IPv4 or IPv6 address directly on the port. We also have our switch virtual interfaces, our SVIs, or simply our VLAN interfaces, where it is going to be the layer 3 representation of the layer 2 bridge domain. So this is typically where we have the default gateways for our servers. And then our third variation is going to be sub-interfaces, 802.1q sub-interfaces for a layer 3 routed interface. So we'll see what type of interface that you use. It really depends on whether the port is dedicated just for layer 3 routing, whether it's going to be shared doing layer 2 extension plus layer 3 extension at the same time. Like you can have an L2 out and an L3 out on the same physical port, but then you're separating which is which based on the VLAN encapsulation. Okay, so doing like a layer 2 trunk link. And then the other option is that we can do VRF Lite, which is to basically extend the tenant or essentially the customer routing tables from inside of the fabric to the external layer 3 routers, or basically the WAN edge, so that we can get the multi-tenancy devices access to the public WAN like the internet, but also keep traffic separation of the internal customers. So most examples, as you'll see in the documentation, they talk about the tenants like Pepsi and Coke. So you want to keep their traffic separate. So if we want to maintain that as we go out to the layer 3 edge, we don't want to have separate physical links necessarily that are dedicated to the individual customers. So we can essentially use just one or more, like a physical layer 3 interface or a physical layer 3 port channel, running multiple sub-interfaces that are going to be shared via multiple tenants. Now we'll see that from the configuration point of view, as usual within the scope of ACI, even though we're ultimately doing the same thing behind the scenes, which is like no switch port or interface VLAN, the configuration steps are going to be much different. And as we saw in the layer 2 section, if you don't know how the objects are connected together, then that's going to be the biggest shortcoming or the biggest hurdle or learning curve to get over in the ACI system. So we'll see that what we're talking about today is really nothing surprising in terms of the result of the config, like running BGP routing or OSPF routing. It's the same type of thing that you would do on regular Catalyst or standalone NXOS, but of course the syntax to do that and the GUI objects to do that are going to be what's kind of complicated and not very self-explanatory, some of the terminology that's used in the system. Now, the first term that we have, which is similar to what we looked at in VXLAN and specifically the BGP EVPN VXLAN implementation, is what we call the border leaf. Okay, a border leaf is basically going to be a normal leaf switch, but in addition to having connectivity to the spine switches northbound okay, over the fabric interfaces. It's also going to have connectivity to our layer 3 devices like our WAN router, our layer 3 switch, firewall, load balancer, whatever, southbound towards the access interfaces. So in terms of hardware capabilities, there's nothing special about the border leaf. So any of the border leafs can be, or any leaf node can be configured as a border leaf just based on its configuration. And we'll see specifically what the ACI system calls this is the L3 out. Okay, so L3 out is basically going to be the construct of the objects where we're taking our endpoint group, which endpoint group is basically just a collection of either IPv4 endpoint addresses or IPv6 endpoint addresses. And then when we're doing the classification based on our security policies, like are you allowed to hit the web server at port 80, 443, are you allowed to ping, telnet, whatever, we need to group the traffic together, essentially like to say, as my public clients come in from the internet, what type of services are they allowed to hit inside? And the way that we do that is based on this L3 out construct. Okay, so it's essentially mapping traffic to from the external network to an endpoint group that we can then use for classification inside of our contracts, inside of our subject and filters. Okay, so we'll see that L3 out is specifically going to be where our edge routing protocols are going to be configured on the border leaf switches. Now, in terms of the type of routing that we can do, again, nothing surprising here as compared to like standalone NXOS mode or pretty much any other platform you're probably familiar with. So we can do static routing, both for IPv4 and IPv6. We can do internal and external BGP, both for IPv4, IPv6, OSPF version 2, OSPF version 3, EdgeRP for IPv4 and for IPv6. And then in the newer versions, you can also do protocol-independent multicast if you want to tunnel multicast traffic over the layer 3 overlay, where in the version that we're going to be looking at in the GUI, it doesn't support layer 3 multicast across the overlay. It does support layer 2 multicast, but essentially when we're configuring the layer 3 out in the newer versions, you would just see a new checkbox that says PIM in addition to BGP, OSPF, and EdgeRP. Okay, so we're basically going to look at all of these options for IPv4 routing, and then we'll come back later when we're talking about IPv6 in a separate section. But really, there's going to be no main difference in the configuration, just the format of the address when we're doing IPv6 routing as opposed to IPv4. Now, one of the big key points that we'll see here with how the layer 3 routing works on the ACI is that we talked about how the construct of the tenant works, kind of the overall container object for both our networking configuration, but also our policy configuration. And the main idea is that by default, the different tenants are not going to have connectivity to each other, simply based on the fact that they're in different routing tables, or more specifically, they're in different virtual routing and forwarding instances, or VRFs. So what this means is that when we're routing to the outside, this layer 3 routing is also going to be VRF aware on a per tenant basis. So when we extend the layer 3 network, like if we have a centralized WAN router, could be like a Nexus 7K, could be like an ASR 1K, 9K, whatever, we can have multiple interfaces where one is dedicated to a per customer basis. So whether these are separate physical links or separate logical sub-interfaces, we need some way to maintain the separation of the layer 3 routing table as we exit the fabric. So what this means on the back end when we do our configurations is that if we're configuring OSPF, for example, we would need to configure OSPF multiple times depending on how many different VRFs and how many different tenants that we have configured. So if we have 100 different customers with one VRF each, it means that we're going to be running 100 copies of the routing table and 100 copies of the routing control plane. Okay, this is going to be true both for OSPF and for EdgeRP. For BGP, the protocol is natively VRF aware, so we're going to have one global BGP process for the overall fabric. And then when you peer with it with either iBGP or eBGP, we're still going to be doing the VRF separation, because we'll see behind the scenes the ACI is going to be doing the peering inside the IPv4 unicast VRF address family or the IPv6 unicast VRF address family as we leave the fabric. So even though it's one global BGP process, it's still going to be separating the routing table on a per VRF and a per customer basis. Now, the way that it specifically does this behind the scenes is with multi-protocol BGP or MP-BGP. And for those of you that are already familiar with how MPLS layer 3 VPNs work, it's basically going to be the exact same thing in the case of the ACI. So the overall logic of that from a kind of a high level is that if we have our external router, and let's say on the router we have two different subinterfaces. We have a subinterface that is for tenant 1. We have a subinterface that is for tenant 2. And then both of these are going to the same leaf switch. Okay, so let's say this is going to leaf 101. And again, these could be either logical subinterfaces, they could be physical interfaces, they could be SVIs that are sharing a layer 2 trunk link. But from a routing point of view, these are going to be separate logical constructs on the back end. Okay, so in tenant 1, let's say that we have network A that we're advertising, and in tenant B, or tenant 2, we have network B that we're advertising to the leafs. So when the leaf is receiving this route, regardless of whatever protocol that it's running between the leaf and the external layer 3 device, so basically on the L3 out endpoint group, we're going to take these routes as they come in, and let's say, for example, that we're running OSPF to tenant 1. We're going to take these OSPF routes in, and then on the back end, we're going to be redistributing them into the BGP process. And BGP specifically is going to be running with the spines. Okay, so let's say, like in our case, we have spine 201, and then spine 201 is going to be connected down to one of the other remote leafs. So we have leaf 102, and let's say that on leaf 102 we also have tenant 1, where we're trying to connect to another layer 2 domain, another layer 3 domain, etc. Basically, what's going to happen is that the routes get redistributed from the edge process. Okay, which in the case of MPLS, you would call it your provider edge to customer edge routing protocol. In our case, it's basically the protocol running inside the L3 out. And you can think of the border leaf as the PE router within the scope of the MPLS network. Or basically, it's the device that's running multi-protocol BGP on one side, and then it's running the VRF-aware routing process on the other side, whether that's an IGP, like OSPF, or whether that is either internal BGP or external BGP. So we're taking the routes in from whatever the external layer 3 network is. The ACI is going to do an automatic redistribution between the processes. So we go from OSPF to BGP and then back. And then when they go to the spine, and since the spine doesn't really know about the final destinations, it's only participating in the underlay routing, which is going to be routing the traffic between the loopbacks of the leafs, or more specifically, the VXLAN tunnel endpoints. It means that we need to some way encode the routes so that we can use the spine to host the control plane for them. Okay, so it's going to be a BGP route reflector for multi-protocol BGP, but we don't want it to have to participate in the lookup of the customer information, like the MAC addresses or the IP addresses that are actually inside the routing table. And the way that we're going to do that is by encoding the routes into either VPN v4 BGP or VPN v6 BGP. Okay, which, like I mentioned, is going to have the corollary to the MPLS layer 3 VPNs. Okay, so we'll see specifically behind the scenes, what's going to happen is that the leafs are going to appear with the spines. Okay, so one or more spines are going to be configured as the BGP route reflectors. And what this is going to allow us to do is to cut down on the number of control plane sessions that we would have to run on the fabric in terms of the BGP peerings. So let's say, for example, that we had 100 leaf switches and we want to exchange all the customer information. If we're running internal BGP, the normal restriction of iBGP is that you have to have a full mesh of peerings in order to advertise all the routes between the devices. And the end result of that is a scaling issue that you run into, which is described by n times n minus 1 over 2. Or in other words, like I said, if we had 100 leaf switches, it would mean that we would have 100 times 99 over 2, or basically about 5,000 BGP peering sessions we would need to establish in order to advertise all the information between the leaf switches. So since in the case of ACI, we're already building the network in a physical leaf spine leaf topology. So as we enter leaf 101 and we want to exit on leaf 102, we're going to have to physically transit the traffic up to the spine switches. it makes sense to do the BGP peerings based on that physical topology design. So the leafs are going to have one or more iBGP sessions with the spines. Okay, we'll see in our particular example, since we only physically have one spine, we're just going to have one BGP session per leaf. We're going to receive the routes in from the external layer 3 network, redistribute them into multi-protocol BGP, advertise them from the leaf up to the spine. Spine is going to reflect them with VPN-v4 or VPN-v6 iBGP down to the other leafs, and then the other leafs can import those routes into their tenant routing table, depending on the VRF separation and depending on the import and export policy that we configure under the tenant object constructs. So we'll see that you can leak traffic between the VRFs, and it's actually much more straightforward to do that in ACI than it is on your standalone Nexus or standalone iOS platforms, because you don't need an external router to send the traffic up to and then back down in order to leak the traffic between the tables. The way that we do it in ACI is simply by configuring a contract from one tenant to another, or from one tenant like into the global table like the common VRF, and then it automatically is going to advertise the routes back and forth depending on the direction of the contracts that we're specifically configuring. So in our first examples, we're going to look at just routing within the tenants, and then we'll talk about later what are some of the more advanced designs we can do, like we have maybe the internet default route in the common VRF, and then we're leaking that to the individual customer VRFs, to the individual tenants, and then also how we do shared services. Okay, so like I mentioned, mutual redistribution is going to happen between the multi-protocol BGP process and the external protocol. Okay, so if we're running OSPF from the border leaf to the external router, we're going to learn the routes in OSPF v2, redistribute them into BGP. They go up to the spine, reflected down to the leafs. Then the leaf is going to redistribute that from the BGP process back into OSPF or back into whatever protocol that we're running. Now you'll see that not all combinations are available in all versions. So if you're implementing this in production, you need to check the release notes on your particular software code to see if it does support that individual combination. In the newer code as of 2.2, pretty much most combinations are supported, but we're running a little bit older than that. We're running 1.3. So the variations that I'm going to show are going to be supported, but not every possible variation that you would potentially configure. So there's a couple different links that I want to mention here before we move on into the configuration. And let me go ahead and open them up. Which the first one is APIC Layer 3 outside for tenant networks. And this is under the ACI documentation under troubleshooting tech notes. And it talks about just kind of the general construct of how we configure the Layer 3 external connection for the tenants. You can see here it says how to do it from the GUI, how to do it from the CLI, and then how to do it from the API calls, okay, assuming you're doing some sort of automation, okay, from the REST API. And then there's also a second document here, which is transit routing, which means that traffic is going to be coming in from the external Layer 3 domain, and instead of going to a server that is directly attached within the ACI fabric, so like a bare metal machine or a virtual machine on ESXi or KVM or Microsoft Hyper-V, we're going to be coming in from one leaf, transiting through the spines, and then exiting out another leaf to another routing network. We'll see there that this is supported in, like I mentioned, not all of the code versions. And then also if you look at the supported transit matrix, this is going to tell you what particular code release that the features are available in. Okay, so the ones with the X's means that it's not supported in. It's just not supported. Okay, yes, of course, means that is supported, and then it tells you what specific sub-release that is available on.